Assalamu alaikum. Today, inshallah, we will continue our previous subject, propositional logic. Okay. Let me share the screen. I think it will be a better idea. Okay. Last time we stopped here, the implication or conditional statement. Let me open the previous one and make a very fast revision because we need all the terms this time also. Okay, after giving some introduction, last time we start to speak about propositional logic, and we give some examples for logic operators like negation operator, and we use for negation operator this symbol, and then we spoke about conjunction or and. Okay, and as you can see the truth table for and operator, if any of the proposition B or Q true, then if both true, then the result of the operator will be true. If any one false, any of the two sides false, the result for and or conjunction will be false. Then we spoke also about disjunction or operator, have this symbol, and in for or operator, if any of the two side proposition true, any side true, then the result will be true. The only case that this operator result is false when you have the two side proposition as false, like here, then the result will be false in the truth table. Then we take also implication or conditional statement. This means if B, then Q. If proposition B, then proposition Q. And in this case, implication, we said B we consider as hypothesis and the Q as conclusion. Then we talk the truth table for implication, and as you can see that when B is false, the first one is false, then B implies to Q will be true. Another case, if you have the two sides true, then the result is true. Then you look for B. If B false, then the result will be true for the implication. and we said that it's logically equivalent to not B or Q because it has the same truth table. If two statements have the same logical table, we said this logically equivalent. That's all for last class. I just make or made fast revision for it. Now we continue for another or others operator, and we continue for implication. We have just some terminology or some statements that can describe the implication, because actually implication is essential in discrete mathematics, and it will be used in too much. So it's nice if you know the terminologies or the statements that describe the implication. Then to describe terminologies to describe P implies Q, you can use these terminologies. You can use if P then Q, if P then Q. You can find it in some statements like Q if B, Q if B. Then this mean, oh, nice face here. This mean if Q found or proved, then your hypothesis is true. Okay, another statement starting from P, not from Q. P only if Q, and it's different than another implication, which is double implication. I will mention it later. It's have similar but not exactly. Okay, it's have different meaning. That's one if and only if. This one only if a Q. We will see some examples later. Okay, another terminology can be used to describe implies that P implies Q. It's very direct one. Or P is sufficient for Q. P is sufficient for Q. Another terminology that Q is necessary for P. It's same meaning like this one, but described in another way for English. And this one similar meaning for this one. Q follows F. This from implies that Q follows P. Sorry, Q follows P. This means we mentioned that P your hypothesis. Okay, then Q will follow the hypothesis P. We can take some examples here to apply this terminology or this English statement for implication here. If we have this two proposition P that Alice is smart, this is a proposition. What's the meaning of proposition? Proposition is a declarative statement, and we use some characters here to short this declarative statement. Instead of every time using this statement, and this statement could be very big, we can use only the short one character that identifies this proposition. So proposition, it's a declarative statement. We mentioned it last time. If you did not attend our last lecture, you have to watch the video from our team. Okay. Then P implies Q. We can write it, for example, we will write this statement to describe this logical statement that Alice is smart. Alice is smart. From where this come? It's P. Is sufficient. This implication is sufficient for Alice to be honest, or honest, sorry. Alice is honest, this is Q. Then I describe this one, P implies Q, by this statement that Alice is smart. This P, this Q, and this, that, blah, 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 P is sufficient for Q. Then, that Alice is smart is sufficient for Q. It indicates that we have implication, like here. Another way to write it, Alice is honest, directly, this P, if Alice is smart, this Q, and if means implication. So we use this one, and we use this one. Oh, sorry. Here, Q if P. Q if P. I mixed it. This Q and this P. Then P implies Q. You can write it like this. P, sorry, Q if P. And you can write it also as P if only Q. Let me just check it again. Only if, not if only. Okay, just it's doesn't matter for me. For example, in the exam, if you write if only or only if, I will not make double check for it. So why like this? Because this will be true if my hypothesis will be true. Then Alice will be honest if Alice is smart. This is my logic statement here. Another logic statement here speak about take a Q first as another example. Then Q, turn off your mic. Okay, thank you. Q implies to P. Let me first take not this one, same one. Q implies P implies to Q, and write another statement here. This statement will say that, ignore this just few minutes. I will open it again. Still in the first logic statement, that Alice is honest is necessary for, ignore the English meaning. We speak here about propositional logic and how to write this logic statement from this propositional. Maybe you don't like it as meaning in English. It's okay. For Alice to be smart. You check this statement with this statement. Okay, let me clear few scratch from this screen. Okay. If you look to this statement, we used is sufficient. When we used is sufficient, we put here, oh, where is it? We put here the hypothesis first. Then P is sufficient for Q. Here the opposite is necessary. Using is necessary, we put the hypothesis at the end, okay? Then the result is necessary for the hypothesis. Then here, that Alice is honest. To reach this result, then it's necessary that you have this hypothesis true. Then here I put Q is necessary, this is the implication for P. I cannot, sorry. What you are speaking here, I cannot understand Turkish, sorry. But seems you are speaking with another student, and it's not the place to thank your classmate. Okay, you can send him private, not here. Please don't chat with each other here during our class inside our team meeting, because I need to check all your messages to know if there's any comment. Okay. Okay, now another example here. We take a Q as the hypothesis. Okay, we mentioned before that implication like this. It's conditional statement, and we consider this first term hypothesis, second term conclusion. If you take like this, Q implies to P, then now Q becomes a hypothesis and P becomes a conclusion. I need you not to confuse. The first part from logical implication is the hypothesis, and the second part from implication is a conclusion. Conclusion come from hypothesis or to prove your hypothesis. Okay, so here we take the opposite. This one become hypothesis and this one become conclusion. Now write it. For necessary, we write conclusion first, and this conclusion is necessary for the hypothesis. So don't mix. Here, which one's a hypothesis? The conclusion P. Then I mentioned first P and the hypothesis Q. When I give same one for this example and I used is necessary, then which one was the hypothesis here in this statement? P. Then P come here and Q, which is the conclusion here. Here I take the opposite for this one. I take Q as hypothesis and P as a conclusion. Then that Alice is smart, it's the conclusion now, is necessary for Alice to be honest, which is our hypothesis. Another example, only if we take first the hypothesis, then the conclusion. Then Alice is honest only if, or is honest only if Alice is smart. Then Alice is honest, Q implies to P. I need from one of you to use only if with this statement. With this statement, P implies to Q. use only if. To describe, use this terminology to describe this logical statement, P implies to Q. Okay, I will give around 1 minute. Okay, you ask why statements are not changing. It's changing. You did not focus here. Here I used sufficient. Here I used is necessary. For sufficient, you have hypothesis, then sufficient, then conclusion. Okay, for is necessary, we use conclusion, is necessary, then hypothesis. The different here, you look here, hypothesis here and here was different. This one, sorry. Okay, this one for this. Okay, and this is statement for this one. It's different. The hypothesis here and here, you look, here's the hypothesis is Q. Here's the hypothesis, sorry, P. Here's the hypothesis is Q. So the statement, it changed, but you did not focus here, seems. Okay, Hassan, it's not correct. It's not correct. Hassan, try again. Okay, Abdul Karim, it's correct. And Basmala, it's correct. Why? Here, where is the hypothesis here? Where is that pin? Okay, here. This is the hypothesis. This is the conclusion. If you use only if, you have hypothesis only if conclusion. This is a hypothesis, this is a conclusion. Then if you want to use only if, you will write like this. Which one? Alice is smart, the hypothesis. Then Alice is smart only if only if what? The conclusion. Which conclusion? Alice is honest. Okay, anyway, the most terms that we usually use here, or terminology, if P, then Q. Sometimes we use implies directly. Okay. Any examples we have, we will see this meaning by understanding the meaning. So you need to understand the meaning first to know which one implies to which one. Okay, bidirectional implication. Bidirectional implication, we use this double-side cursor, okay, arrow, double-side arrow. And it's like you said, when you said P double or bidirectional implication with the Q, it's same when you said P is true if and only if. We mentioned only if for implication, but here if and only if a Q is true. So you need the double side, this two side to be true for implication to be true. That's why if P and Q true, then you have the result true. If both sides also false, the result will be true. And we will mention this later because not false and not false here. We have a rule later, law, you will so that there is negotiation rule, the opposite of the false here for implication. To understand this, it's similar like if you said P implies Q and Q implies P. This means take this side and take this side. That's why it's bidirectional implication. Here example, a student gets A if and only if his weighted total or weighted mark is more than or equal 90%. Anyway, the most important here, you have to know the truth table for each of this operator, bidirectional operator, implication, or, and also not operator. We have another operator which is XOR or exclusive OR, and it's also exists in some programming language. You can find XOR or exclusive OR. XOR operator do not have description for itself or terminology for itself, but it's same as when you said double or bidirectional implication and make the negative for it or negation for it. Okay, it's similar or equivalent. This one equivalent for this one. So when P, X or Q will be true, it will be true when P and Q different. So if T and F or X or F, then the result will be true. If you have F, X or T, also the result will be T. If the two sides similar, the result will be false. Similar two sides, then the result will be false. This is the XOR truth table. Okay, as you know, any mathematical operator have what we mentioned a priority. Okay, this is the precedence or the priority tables for the operator. If you have many operators in the same statement, first operator to P calculated will be not, then, and, then, or, then, implication, then, bidirectional implication. Of course, the top priority will be the practice if you have this type of practice. Then, if you have this statement, it means that you have to calculate not P or Q, you have to calculate not P, then get and Q. If you have P and Q implies to R, this means you have to find the result of P and Q, then you find the result for the implication. For example, if the result is K, then you find the implication with R. This priority is very important because later we will see some examples that we have bigger or more comprehensive logical statement. Okay, or we sometimes or we here we will call it compound proposition. Okay, we will take a break after 10 minutes, not now. Okay, continue. How to translate logical formulas or logical statements to English statement. Sometimes you want to describe some English statement by logical formulas. Sometimes after doing some mathematical, okay, applying some mathematical rules or law, you need to translate it again to English statement. So we usually can construct complicated logical formula. We name this logical formula compound propositions or compound formula or comprehensive logical formula. We will use compound proposition. Then you do some operation, applying some rules. Then you want to get the result using English language. Now we will see how to write the formula using English statement. If we have this two proposition, Alice is smart, Alice is honest. We have this formula as P, this formula as this proposition as P, this proposition as Q. We need to translate this formula to English language. Now, read it. It's not P. This means Alice is not smart. Alice is not smart. And usually we translate it to but. Sometimes we translate it to and. It's depend on the word that you use. Or it will be translated to or. Okay, and it could be translated to but or and. Okay, implication, as I mentioned, the most form used or terminology used for implication, if P, then Q. If the hypothesis, then the conclusion. And you have to focus. These names, some people could use K, you use R. It's all names for proposition. You can name your proposition any letter here. So you focus not on P and Q. You focus on that first part, consider hypothesis. Second part, consider conclusion. So to write implication as English, you use if P or if hypothesis, then conclusion. It's same implication or imply, X imply to for P or for Y is similar that implication between X and Y. We name this operator as implication. You could use in English statement P implies Q. Okay, so it's same meaning. Okay, now we translate this. Not P, this means Alice is not smart because P said that Alice is smart. Then not P, this means Alice is not smart. But honest, but Q. Not P, but Q. Q is Alice is honest. You can write it like this. It's all about English language here. You can write it like this. Not P. What's the meaning of not P? Alice is not smart. Alice. I will write same statement here again in another way. Okay, maybe more simple way for non-English speaking people. Alice is not smart and Alice is honest. But if you see the meaning here, it's same meaning, but for English language, it's very poor statement. That's why instead of using this term again, we use this here. To remove this, we use but. This is the meaning of but here. But honest, this means she's Alice not smart and Alice is honest because we used and. So and could be converted in English to but or and. If you write like this in the exam, it's correct and I will give you the marks. But in the meaning of English here, it's very poor statement, yeah, not totally correct in English language. Okay, P, what is P? Alice is smart. Or, for or, we used either or. Let me like this. It's better too. Okay, or we can make it like this. Either P or first part, okay, or Q or second part. Here we have two parts. Let me use another color because we have here red. I will use blue. Okay, we have two parts here. This part and this part. Don't think too much about what inside here. We have or. Then this side, either this first side or second side. Now second side, we want to first side P, yes? So either Alice is smart, or now think about the second side. Not P, not P, what is not P? Here P, or not B, not, sorry, P means Alice is not smart. Okay, smart. Okay, not B, this P, and Q. Q, it's direct, Alice is honest. And P, then, or this come from here. Now, not P and Q. Alice is not smart. Not P, Alice is not smart. This P, yes, this not P. She, what, who's she? Alice, okay? She is not smart. I said that. And we use but, okay, to describe and. But honest, or but she is honest. But she is, or but Alice is honest. Okay. Now we have implication, we have hypothesis, we have all this as conclusion. To write the implication, we write if hypothesis, then conclusion. Yes, if what hypothesis we have? If P, what is P here? Alice is smart. Then if Alice is smart, then the conclusion here, not Q, not Q. Alice is honest. Q is honest. Then not Q means Alice is not honest. Okay, then what conclusion here we have? Alice is not honest. It's the conclusion. Then if hypothesis, which is Alice is smart, then she is not honest. she means Alice. Okay. Then Alice is not honest. It's the conclusion. Like this, we can translate the logical formulas to English. Of course, you need to read more examples. You need to read more examples from the book. Okay, we highlighted the parts from the book that we have examples or we take during this course. I think this around page 20, page 25, like this in the book. Okay. Now we can take around. Okay, let us take the opposite. Then we take a break. Okay, to start another part. Now the opposite, translating logical formula from English. We have English language and we want to translate or get the formula from this English language. Okay, same, we have same two proposition. P, Alice is smart. Q, Alice is honest. And we have this statement to describe using English language to describe the formula, and we need to extract the logical formula. Let's first analyze this statement. Alice is either smart or honest. This means we have or, yes? I said either or. You have, of course, in the middle here, this is the or statement. Yes, Alice either smart or honest. Here we have smart, which is P, or honest, which is the Q. Then this is the first part. Alice either smart or honest. But this meaning and, yes? But Alice is not honest. Alice is not honest. This means not Q. If she is smart, she is smart, this P. Now, if you return to our original statements here, when you let me just clean this. When we used if, this means we have hypothesis implies to conclusion, and we used if, then we have conclusion if the hypothesis. Yes, then first part before the if will be the conclusion, and after the if will be hypothesis. This is the best way to understand it. Why? Because sometimes you have another letter, maybe K, maybe R, maybe T. T cannot be T because we have T and F for true and false. Okay, so it's better to understand it using conclusion and hypothesis. Okay, so if you have F, just F, then the part before F will be the conclusion. The part after F will be the hypothesis. It's different than if then. For if then, first part will be hypothesis, second part will be conclusion. Using only if, first part also will be hypothesis, second part will be the conclusion. Okay, then we return to our example. I think we here. Then, when I said if, first part will be conclusion. Conclusion come after the implies here. And hypothesis come before the implies. Then, this means P implies to what? To not Q, because not Q completely here. Okay, then, and here but means and. Let me write this with using different color to connect between all of them. Okay. I will use different color here, maybe using red, but this red. Then this one, P or Q. And this one, and this part, all this part, we using F here, means if we take this part, not the Q, and this part P, from here we know this, then this meaning P implies to not Q. Connect all the parts here in the red, then you have P or Q, and P implies to not Q. Okay. Let's use same way to translate the second example. I will use first a blue, then I will use red. Okay, that Alice is smart is necessary. I mentioned before, is necessary take conclusion is necessary, and then you have hypothesis. So when you convert it, you will convert it to implies, and you take before the implies the hypothesis, after the implies the conclusion. You see, this at the end come here before the implies because it's hypothesis, and first part become after the implies because it's the conclusion. Then Alice is smart. This one P is necessary and sufficient. Necessary and sufficient. Sufficient is another thing. When you have sufficient, this means you have hypothesis sufficient for conclusion. Then if you write implies, you take first part, then second part. And this mean what? The and mean and. Then here you have two implication, because we have is necessary and we have sufficient. Then we have two implication here. This is the first implication and second implication. Let's understand what to write in the first implication and what to write in the second implication. Then the result will be and we have here implication and we have here implication. Now, Alice is smart, this P. Alice is honest. Is Q. Then for is necessary, we take the opposite, yes? We take conclusion first and hypothesis second. Conclusion, then hypothesis. Here, you see, I always return to this until you can memorize it. For is necessary, you take conclusion. Here I said conclusion, so you can always use it, and hypothesis. For this statement, conclusion is hypothesis is P, conclusion is Q. So the difference between is necessary and is sufficient, here you take hypothesis, then conclusion. Here you take conclusion is necessary for hypothesis. Okay, same as I mentioned here in this example. Is necessary, conclusion, then hypothesis. Sufficient for hypothesis, then conclusion. Then here I will take Q implies to P, because Q is a hypothesis here for this one. And this statement, the hypothesis will be, here we mix the hypothesis and conclusion. It's the opposite for sufficient. P implies to Q. And between both will be and. It's similar, like if you look here, it's same like this one. Then you can write it directly after that when you see that you have both sides. Q implies to P and P implies to Q, it's equivalent to bidirectional. Okay, so when you see bidirectional and you want to use it, you can write it like this to improve it later when we speak about the improve. Okay, so this you have to know that P bidirectional or two direction Q, it's similar like Q implies to P and P implies to Q. We mentioned that it's logically equivalent. We will use this symbol for logically equivalent. Okay, we take a break, only 10 minutes, then we return inshallah to our class with some other examples about logical equivalent and some proof, using here some laws and some proof. 10 minutes break. Okay, we continue our lecture for today. How many students are around now? Please raise your hand. Okay. Of course, I will use video to get the names. Okay. Every class I will use. No, not your video. I mean, I will use my video here after. Because it's like this. Okay, I mean, we are recording the video. Then later, I will watch the video and get the names here for attendance. That's what I mean. Not to open your video, okay? Okay. We continue now. Tautology and logical equivalence. What's the meaning of tautology? When the compound proposition means propositions like this. Compound this one because have many propositions. Okay, we named it compound proposition. If you have compound proposition and it's always true, then this compound proposition called tautology. Okay, then tautology, a compound proposition that is always true. For example, when you mention not P or P, this compound proposition always true, because if you take the truth table, P, you can take it true and false. Not P, false and true. So if you make or between them, like this, or, P or Q, or not P, sorry, the result always will be true. Also, if you take not P or P, the result always will be true. So if you have some compound proposition like this that is always true, we call this tautology. Two propositions P and Q logically equivalent if the truth table will be the same. If you have two compound proposition, if you have two simple proposition or compound proposition that have the same truth table, then it's both logically equivalent, and we speak about logically equivalent last lecture. P and Q are logically equivalent if P double implies Q. And its tautology will be Q implies to P and P implies to Q. What's this meaning? I want to ask you, Q implies to P and P implies to Q. Is it true or false? It's true because it's tautology. Logical equivalent. Logical equivalent, we use this symbol. Later we will see this. We will see a lot of flaws here, and we need to memorize this laws. Here's the symbol for logical equivalent. Then, if you have two proposition or two compounded proposition, big proposition, then this term used for logical equivalent. Okay, here some examples for logical equivalent. Here we want to prove that P implies Q is logically equivalent with a Q or not P. This means we want to prove this. P implies Q logically equivalent with Q or not P. The simplest way to find this or to prove this using truth table. Using truth table. If you have two compound propositions with the same truth table, then it's logically equivalent. Then we need to find the truth table for first side and the truth table for the second side, and if it's same truth table, then it is logically, they are logically equivalent. Okay, now let's find the truth table for both sides. Here we have P and Q, and we mentioned that P implies Q will be true in two cases. If you have the two sides true, or if you have your hypothesis false. So two sides is true, the result will be true. The hypothesis, which is P here, false, then the result will be true. Okay, what about Q or not P? Let's first find not P. We have P, true, true, false, false. Not P will be false, false, true, true. When you use not, then true become false and false become true. Now, or, what is doing or? If you have any side true, then the result of the or will be true. Okay, now true or false, it will be true. If any side is true, the result is true. False or false, the result will be false. True or true, the result is true. False or true, the result is true. If any side is true, then the result will be true. If both side false, the result will be false. Okay. Then, if you look here to the last column, this column and this column, you will find this two columns identical, have the same result. Therefore, this two proposition logically equivalent. We can write it like this. P implies Q logically equivalent with Q or not P. Then, what tautology we have here? We have here this tautology. If you convert this to double implication, this is logically equivalent, yes? And you can find from this logically equivalent, you can find tautology. What is the tautology? Tautology, it's a compound proposition that always result true. So, the tautology here will be P implies Q, the first side, and we change this logically equivalent to bidirectional implication, Q or P. I need someone to mention for me this tautology will result true or false. How many one focus with me? Of course, true, because I said this tautology always result true. Here, you have to focus. Compound proposition that is always true is called tautology. So, when I found logically equivalent proposition, I can make tautology from it by using implication between the two equivalent compound proposition, and tautology always result true. Okay, another example. Let's solve this example with each other. Okay, I did not solve it before, so we can solve it with each other by using truth table. Prove that P, X or Q. This you can read this P X or Q. Logically equivalent. Oh, why is this move back? Logically equivalent with not P double or bidirectional implication with the Q. Okay, let's now find the truth table to prove this. What is the truth table for XOR? XOR, if the two sides different, the result will be true. If the two side different, the result will be true. If same, for example, P and Q true, then the result will be false. P and Q false, the result will be false. Only if P and Q different, then the result will be true. Then P here true and Q true, then the result will be false because they are same. T and Q different, this means this is true. P and Q similar as different, then it will be true. And if it's same, then the result will be if. Then false, true, true, false. Okay, this is the XOR. I already mentioned here, but I know some students maybe did not focus. Already mentioned here. If two sides similar, then the result will be false. If two sides different, the result will be true. Okay. Now about the implication. Double or bidirectional implication. Look, for bidirectional implication, if the two sides similar, the result will be true. If the two sides different, the result will be false. It's the opposite directly. Then we have P and Q similar, then the result will be true. We have P and Q different, then the result will be false. False because different. Here similar, then true. Now we need to make the negative for P double implies Q. This the negation. This means if true become false, if false become true. Then this one true, it will become false. This one false, it will become true. This one false, it become true. This one true, it become false. So because this the negative for this one. So you look to the last column here and here. Is it identical? Yes, it's identical. Then we proved that this logically equivalent. I want to ask you, P not XOR, sorry, Q bidirectional not P bidirectional Q. Is it a tautology? I think the spelling only. Okay, here U, not here. Okay, is it a tautology or not? Yes, it is. Why? Because as we proved here that Px or Q logically equivalent, not P double implication or bi implication Q. So because this logically equivalent, then this always true. Okay, good. We have too many students focus with us. I'm very glad for this. Okay. Now we will take some Opa. Is it finished, our class? What time our class will finish? Oh, 5 minutes. We still have 2 minutes. Okay, we cannot do too much for this 2 minutes. We still have many things to do. Maybe, okay, we continue next week, inshallah. We continue next week, inshallah, because this subject needs time. Maybe later we will take extra class. I mean, maybe after a week or 2 weeks, we will take extra lecture, inshallah, because we are slow a little bit here. Okay, that's all for today. Have a nice weekend. Okay, but before before exit here, you have some. We finished here this one. Okay, we will stop here, but we have some exercise that you need to. It's not homework. It's not homework. But I prefer if you try to solve this exercise. Exercise 1 to 6 at page 35 in our book. Okay, try to solve this exercise. Okay, try to solve this exercise. Exercise 1 to 6 at page 34. And if you have any question, send me the question using Telegram group for this exercise. Also, if you did not know how to solve any of this exercise, send me any question using Telegram group. Please, not in our next lecture because we don't have too much time during the lecture. Okay? Inshallah next week. Have a nice weekend, inshallah. Assalamu alaikum. Guru Shuruz.